A very, very good morning to all of you ladies and gentlemen. It's a real pleasure to be here in front of you. Going on Thursday morning, 9 a.m. is really, really hard, especially after all the parties I've been hearing about people having last night. So I really appreciate you guys coming in bright and early for my session. For those of you who don't know me, I'm Chetan Venkatesh. I'm the CTO and founder of Atlantis Computing. We're one of the sponsors of BriForum. I'm mostly known for my intense geekiness about storage in the industry. So a little bit about me. I've been in the data center infrastructure space for about 18 years. I've started 3 companies in this space so far, all the way back from 1999 in the mainframe space to 2003, 2004, where I built one of the first server and storage provisioning management software companies. And then in 2007, after that company got acquired, I started Atlantis Computing to focus on the virtualization storage space. Among all my accomplishments, I think I'm most proud of the fact that this is my 5th year speaking here at BriForum. So big hurrah for me, please. Thank you. BriForum is a unique place because I go to so many industry shows. You hear so much of architecture and hype, and everybody selling their technologies like it's the latest thing since sliced bread. BriForum is one of those unique places where people who are truly passionate about technology, about understanding it, about the future, and about constructive problem solving really get together. So it's really great to be in your midst, talking about probably what I'm most passionate about these days. The current transformation within storage. The last few years, storage has taken a dramatic turn. For about 40 or 50 years, we were going along one set of vectors. Oh, you know what? I haven't turned this on, have I?
Now it's on.
Okay, great. So for about 40 or 50 years, we had been going along one set of trajectories in the data center, mostly guided by mainframe technologies. The evolution of network and storage was very much a result of how mainframes were being architected. A lot of proprietariness in the data center, systems that were fully vertically integrated all the way from the client that the user used to access data, all the way to the systems that processed them and the storage that eventually persisted them for long periods of time. But over the last 15, 20 years, with the advent of the x86 architecture becoming more powerful, a lot of things have changed. But storage had remained one of those areas that was untouchable. There were primarily 3 companies or 4 companies that sold practically 90% of the world's storage. And then mid-2000s, virtualization came in existence. Well, virtualization had been around for 30 years, but virtualization really became real on the x86 architecture and unleashed a phenomenal amount of innovation and new capabilities within storage. We're at a cusp today of really transcending an archaic architecture that I'd love to describe to you in more detail. And we're going to go into a whole new era in the next 5 to 10 years, where storage as you know it, and along with it compute, is going to change dramatically. So with that preamble, let me launch into my presentation. One last pointer. So I'm the CTO and founder of Atlantis Computing. And my company has built what is probably one of the first new generation storage systems, which actually allows you to take RAM, random access memory, that's on a server and turn that into storage. And this whole idea of taking memory, and turning that into storage has been termed in-memory storage. And it's a very new field. There aren't many companies, many technologies, but having built Atlantis, I've had a first-hand view of many of the challenges and many of the opportunities that come with that. So really delighted to be sharing some of those perspectives with you today. I love to keep it interactive, so if you have questions, feel free to raise your hands, shout, yell, scream, whatever makes you feel good. So with that, let's get started. We're going to take a little journey today, and I appreciate your indulging me because I really like to start at the very beginning. So I'd like to spend about 15 minutes setting context as to how things got this particular way. I'd like to talk a little bit about why the world is the way it is. What is it that within our biological systems creates things like Facebook? So we're going to take a little journey actually starting inside of biology. And from there, we're going to look at how that extended to human beings creating civilization, and with that, how computer storage became a necessity. So it's going to be pretty interesting. Indulge me. It's probably 99% all wrong. It's my interpretation of how the world works. But at the very least, I promise you it'll be entertaining. Once we've sort of set a context for where we are, we're going to talk about where storage, where virtualization is today, how these architectures work today, and what are the great challenges that are there in the way of this becoming even bigger. Because I really think that today we're at a wall. Our current storage architectures are not well understood. People are deploying virtualization at large scales. They're building clouds, whatever that term might mean to you. But fundamentally, there are some inherent deep DNA level challenges around storage within the stack that most people don't know about. And I'd like to share and discuss those with you, because I think unless we transcend them, we're going to hit a wall. And that wall can only be breached by spending a lot of money, by making a very select few set of companies paying them a lot of money. So it's a very interesting set of challenges that are over there. And once we've done that, and we talk about what are some of the solutions in that space, specifically around what in-memory storage can do for you, we're going to talk about tomorrow, which is my favorite part, because I come up here every other year to BriForum, and I say a bunch of nonsense about what will happen in the next 5-10 years and get people to write about it on their blogs, which is really great. But today we'll specifically look at the next 5, 10, 15 years and look at some of the technologies that are on the horizon and how those are really going to change our compute storage paradigm completely. So if you are a decision maker who's in charge of making bets on your company's infrastructure, the future part is something that I'd love to have a dialogue with you about. So let's start on part one, context. So we're going to talk a little bit about biology. We're going to talk a little about a history of storage starting in literally 5000 BC. And then from there, fast forward all the way up to the modern data center. So it'll be a quick tour de force to sort of give you an appreciation for what's going on. This is one of my favorite sayings. Those who don't know history are destined to repeat it. And if you look at this next section, you'll actually find that we're doing things that were decided 5,000 years back. It's quite fascinating, some of the things that are happening over there. There's a very interesting anecdote that I'll share with you. So the modern railway system has a gauge width of 3.5 feet or 4 feet or something like that. And the reason it's 4 feet is because that's what the British did. They invented the modern rail system. And why the British did that was because when the Romans built the roadways, when they conquered Britain, that was the width of the chariot path. And as chariots ran on those roadways, they made grooves in the stones, and so there was a groove, in all these roads. And unless your chariot wheels sat exactly in that groove, right, they would break off. So essentially, then the question goes, why did the Romans decide that that should be the width, 4.5 feet? It turns out that that's exactly the space that's required to accommodate the rear end of 2 horses. So if you fast forward all the way 5,000 years, our specification for railroad transport, which says that the gauge width of a track should be 4.5 feet, proceeds all the way down to the Roman era and is determined by the width of 2 horses' asses. So, so there's a lot of that going on in storage, by the way, no matter what you think. You're buying that great flash array, good luck to you. There's a little bit of that Roman stuff going on there too. So there's 2 horses involved somewhere. Thanks, yeah. So let's start over here. And don't read through the whole thing. I'll read it out for you, don't worry. So I'm very fascinated by the human brain. I'm fascinated by storage technologies of all sorts, and I think the one that's the most incredible is the human brain. And I spent the last few years trying to understand and study a little more about it. And at the heart of it, if you look at what the brain is, it's a symbol processing machine. And human beings are incredible in that we can take anything that we experience and turn them into symbols in our brain. So for example, if I spilled some coffee on myself, I can create, and I got burnt as a result, I can create a bunch of symbols around that. I can create a symbol around coffee, I can create a symbol around the experience of pain, and I can create a symbol around whatever that accident scenario was. Maybe I walked into a wall, I tripped, I fell, etc. And so we can literally take anything and turn them into symbols. I mean, here we are, you and I having a conversation, and I'm essentially uttering a bunch of gibberish. They're just sounds, yet each of those sounds has potent symbols associated with it that we as a culture all agree on, right? And as a result, you can understand what I'm saying. It is astounding when you think about what's going on actually beneath the surface. This to me is cracking open the matrix. If you go into the matrix and try to find out what it is this, that we're basically a bunch of gigantic symbol-making machines, meaning-making machines, and we can create symbols out of anything. The beauty of symbols is that they nest and they encapsulate. So I can take some simple symbols, put them together, and make a more complex symbol, right? I can take a symbol saying, this man is my dad, this woman is my mom, put those two together and create a symbol called family, right? And that family symbol can have other attachments to it, relationships, right? Aunt, uncle, cousin, so on and so forth, and the symbol keeps growing. So there's this massive nesting and encapsulation capability that comes with symbols that makes all of human life possible. And ultimately what the human brain's doing is it's constantly pattern matching symbols that already exist, creating new symbols for new experiences that are happening. So it's essentially creating, modifying symbols. You change your belief system sometimes, you change your opinion about things. It's erasing some of them. You might hit your head really hard on something and things get erased. Or you might actually try and erase them willfully. That's also possible. So it's pretty amazing the organic infrastructure that human beings have that allows them to do this. So if you look at what's possible is that we can create, we can store, we can recall, we can modify, we can combine, and we can erase. And so from a storage perspective, many of the fundamental aspects of storage, right, are something that you and I inherently do. My 2-year-old daughter inherently does. It's just we're biologically wired to do this stuff. And it looks amazingly like computers and storage systems if you think what's going on. And so if you look at the history of humankind, we've created more and more complex symbols to describe our lives. But the most interesting aspect of symbols is the fact that we can actually communicate these symbols to each other. So I can say words, and as long as we have a common dictionary of sounds, you understand what I'm saying. I can even make funny little squiggles, and as long as you agree on what those squiggles represent, and we have a common understanding of those symbols, right? You can even read my thoughts, and you can hear my thoughts, and it's an amazing way of actually sharing state information between people. So symbols can be communicated. That's the power of symbols. Symbol manipulation can also be codified via instructions called algorithms. So for example, I can take I can describe to you how do you set up Virtual Center along with along with Windows Server 2012. And here I am taking a highly sophisticated, complex, nested set of symbols, right, and telling you how to manipulate those symbols in your brain, which actually map to other symbols within a computer system, and you're able to pull this off. So it's incredible, this human machine that does this. No other species on this planet has this particular capability. And this is why we have a storage problem. Because we inherently love to grow and create additional symbols. Languages evolve over time. Our ability to share ideas and thoughts evolve over time. And so since the dawn of time, we've essentially been trying to communicate, and over-communicate to the point now that we have things like Facebook, where we can literally communicate every nonsensical, mundane thought or activity that we're doing. And it's become so efficient. So it's quite incredible, what happens. The whole intent of communication has been to, transfer knowledge from one generation to another. But in our era, it's a very special time in computing because we can literally not just transfer knowledge between our generations, me and my kids and so on and so forth, but we can communicate with each other. Over the last 10 years, I've found that I used to read voraciously. I used to read about 25, 30 books a year. I read one book last year. 99% of my reading came from Twitter because of people posting links on Twitter saying this is worth reading, that is worth reading. And I think I'm a far more knowledgeable person today than I was 10 years back. And I know how to apply that knowledge even better because of this ability to use these modern tools and technologies to pass along these symbols. So one of the incredible things about symbols and codification of symbols, which is making them more permanent, is the fact that when you codify them, you give them temporal existence, not just spatial existence. So what I mean by that is, here I am talking to you today. we're sitting in an auditorium and we're spatially in the same location, and I can talk with you and you can talk with me and we can share our symbols with each other. But without the ability to do codified symbol communication, which is writing, there's no ability to actually do this in time. So one example is they're recording my video. And by recording my video, you can play it back 5 years from now and still get the content that I was discussing over here. So this ability to communicate is extremely important because we've now been able to allow our communication to not just be bound by spatial boundaries, which is the way it was for thousands of years, but now you have also transcended into temporal boundaries. You can actually have your communication go over time. And we have communications from thousands of years back. We have the Bible, we have the holy books that have brought a lot of our culture with us over the last few thousand years. And now with the advent of the internet and the ability and the NSA saving every single word that you say, right, our symbols will be saved for God knows how long. Frankly, I don't give a damn because it's not going to be very interesting. 99% of the stuff that I talk about is completely boring and mundane crap, so I don't know what use this would be in about 50 years, 100 years. But it's fascinating to know that our ability to transcend temporal limits has been completely completely created at this point. So ancient storage devices, when you look at these things, you don't implicitly think of them as storage devices, but early human beings really wanted a way to break that temporalness, spatial nature of communication, and so they tried to invent script and write it on media that had some semblance of permanence. So they used things like clay tablets, for example, and in China they used bones. The problem with clay tablets and bones is that they're very, very heavy. And as a result, even though you could keep some, you could chip on a rock and keep that information there for a period of time, people needed to actually come to that rock to be able to read it. So it wasn't exactly the best way to break the spatial boundaries. So the Egyptians actually came to our rescue because they invented papyrus. And papyrus and parchment were two lightweight ways of taking our codified symbols, our writing, and being able to transport them. And if you look at the history of human civilization, our ability to connect civilizations together, connect societies together, mix and match ideas, it really comes from this ability to take our words and our thoughts and share them with each other. And so one of the most important forms of communication in those days, from a storage standpoint, was parchment. And the fact that parchment was easy to fold, that you could put it on horseback and could transport it by horseback. And ultimately, the ability to aggregate parchments became the notion of books, and books became libraries, and we had the codification of writing and our knowledge in some magnificent ways. Now let's get into a little bit of the geeky aspects of this. So if you're a storage engineer in 500 BC, right? Not that you call yourself that. These are sort of the challenges you would have, and you're trying to invent new storage media. Your biggest number one challenge is, most people don't share your language because people are isolated. And there is no standardization of these sounds that are coming from my mouth. Those sounds are probably understood by those who are in my immediate vicinity all the time. But for people who get further and further away, it sounds more and more like gibberish. So there is no standardization. There are no protocols to communicate. Big problem, right? And the second problem that we have is that the media that I'm using is not durable. I wrote on a clay tablet. The next day my dog went and took a little piss on it and it's all gone. So durability is a big challenge. There is no durability in this data. The challenge also I have is that these clay tablets are really heavy, and so the amount of data I can actually record on them and carry in 1 unit of space is extremely small. So if I had 5 kilograms or 10 pounds of clay tablet, each tablet weighing a pound, I could barely write about 16 kilobytes on each page, 16 kilobytes worth of data on each page. So for about this much of space, I'm carrying about 160 kilobytes worth of data between me. There's not much you can communicate with 160 kilobytes of data, and that's the fact that all the storage companies are exploiting when they sell you these massive storage arrays. The problems haven't changed actually, and even if you use papyrus, you had other problems. Like for example, your papyrus would rot, it would tear. So as a result, you had to do something called copying. You had to make multiple copies of each of your documents. You had to make backups. So these concepts and these terminologies that we use in computer science and virtualization, they're ages old. They're 5,000 years old, because even 5,000 years back, they were dealing with data consistency issues, redundancy issues, durability issues, and media consistency issues. And your data transmission was done on horseback. Terrible latencies, I'll tell you. You just don't get good latencies on horseback. You get decent bandwidth, but you get terrible latencies. Now we're going to jump. So this was the case for almost 3,500 years, and right after the Dark Ages, post-Renaissance, there was a burst of scientific activity around the world. People were free to think and create. And some massive jumps in transmission started to happen. We're still dependent on papyrus. We're still, making books, etc. But there was a massive jump in our ability to transmit our knowledge to each other. So, for example, the biggest one that happened was this thing called the Semaphore, where we started to use a bunch of symbols, like me raising my hand like this, and we still do this in football games, right? Semaphores, to communicate symbols that represent an idea. And so the idea was very simple, take a set of symbols that represent other symbols, and transmit them over long distances, usually by line of sight. So smoke signals, for example, was one way they did it. The Romans actually had optical technology at their disposal. What they did was they had massive mirrors put up on hilltops, and they used those mirrors to flash lights, and a series of patterns would denote if an enemy was coming or not. But the biggest limitation with these technologies was, just like with microwave, line of sight issues. If you couldn't see the other guy that you were transmitting to, there was no way to actually transmit to them. So this was solved in 1809 by a guy called Sommering, who's a Bavarian, a German, who invented the first electrical semaphore. And what he did was quite interesting. He basically hooked up a bunch of batteries to a dish full of water with cabling into that water, and every time he created a circuit, the water would break down into hydrogen and oxygen, right? What do you call it? Electrolysis. And he would actually measure the amount of gas that filled the test tube to figure out what it meant. So if it created, say, 1 cubic centimeter of gas on the oxygen side, that meant yes. If it created 1 cubic centimeter or 2 cubic centimeters of oxygen, it meant no, something like that. So you can imagine, again, now we have the ability to transmit our thoughts, albeit in very, very simple, short bursts of binary information, yes, no, blah, blah, blah. But we're starting, the human being, the Homo sapien culture is starting to transcend these limits that we have around distance using this. But a man called Samuel Morse was really the guy who sorted this all out, because he invented the Morse code. And he also invented, along with it, electromagnetic impulse, the ability to send electrical signals using an electromagnetic device across a wire. And so the famous dot and dash system that he invented became the basis for us to be able to transform and communicate our symbols over very, very long distances. So, there are literally thousands and thousands of inventions like this, but I'll just touch on, one or two that are of note. The reasons I'm touching on them are, these are inventions that allowed us to take audio and visual communication, what we do as human beings, and somehow give them the ability to permeate time and space, the ability to persist across time and space. So photography, another great one. Up until this point, we had to sit and hand draw, scenes that we saw, or things that we liked, or we had to carve statues. And this man, Niepce, he came along, invented photography, and allowed us to now take our experiences and create bitmaps out of them, right? Typewriter now allowed, the printing press had been invented, but it was a big monolithic invention. Now the typewriter came about and democratized the whole thing, because people could publish documents on their own. I mean, I'm pretty sure that people, when they got the typewriter in 1867, were as excited as we are about our blogging platforms. They thought it was going to change the world, because every human being could now, who was literate, could actually now communicate with each other. And then Dewey Decimal System, the ability to organize massive amounts of data in libraries. Probably the most important one, Edison inventing the phonograph. And the phonograph, as you know, is the predecessor of the LP record. It allowed you to make grooves on a surface and then play back the audio content by reading those grooves. I want you to just remember this part, that the phonograph is one of the reasons why we're utterly screwed in virtualization. I'll talk about that topic a little later. It's the physics of the phonograph that have still followed us into the data center, and we'll talk about that piece because it's such an important invention. Recording with phonograph, Edison, and then the gramophone, which was a very, very highly reliable way of getting audio playback. The telephone, of course, 1876 Graham Bell, and then Guglielmo Marconi inventing wireless telegraphy, the ability to actually send these symbols and these codes over the ether, over air, without actually needing any kind of physical connectivity. Needless to say, that saved a lot of capex for a lot of governments everywhere, and that really unleashed the whole transcontinental connection between different cultures. And so these are the things that these guys had to deal with when they were building these transmission systems. It's one thing to sit and have a standardized alphabet and to agree that that's our alphabet and that's how we're going to share information. But if you're going to do this over long distance, you also need to worry about, protocol. So for example, the guys who were inventing these transmissions, one of the things that they came up with was that the symbols had to be laid out sequentially, because that's how we write. We write from left to right, we write from top to down, we write from right to left, whatever it is. Ultimately, it's all sequential. And unless you read everything exactly in the order that it's written, you can't make any sense of it. So, you have to read back in the same way that it was written to have any kind of sense made out of it. Now, here's the challenge. In transmission, you have to transmit it exactly in that same sequential sequence. If you lose pieces of it, people don't understand on the other side, so you have to have error checking. You have to have some way of saying, stop, I didn't get that piece, back up, and play it back to me. And you need also a higher layer of symbols now to manage the complexities that come with transmission. So these protocols that people invented required their own metadata that also had to be encoded as symbols within the transmission systems themselves and transmitted back and forth. And transmission ultimately involved this. We took one set of symbols, which is maybe I'm describing I'm describing a war that's going on in Europe, back to my king or queen, and I'm describing that using a set of symbols. Somebody on the other hand, gets the standard set of symbols that I just described it in, and then, transforms that back to the originating source. So it requires a fair amount of coordination and a fairly large set of dictionaries that are coordinated over there. Now, if you look at a person who designs a protocol, for the internet, if you invented you invented the new chat system, or you ever wrote extensions to Jabber or something like that, this is exactly what you do. And so, we've been dealing with these challenges for a very, very long time. So every time I get smug about having done something really cool, this is what I realized, that somebody 5,000 years back probably already had that challenge and solved it, at much greater odds than I have, given that I have things like the internet. But it's my fundamental belief that the greatest invention yet up until now was this guy, Waldemar Poulsen, because he invented magnetic recording using steel tape. He was the first guy who was smart enough to take steel tape and put some iron oxide on it, and now put electrical charges on specific segments. And he had the ability to spool that tape from one end to the other, and you can actually record audio, video data, and this laid the foundation for data storage. So this happened in 1899, 200 years back, and this is one of those situations. This guy's invention has become the data center's two-horse ass track with gauge. So let's talk about that in a bit. But one of the most pivotal inventions in data center. By the way, how many of you have heard of Waldemar Poulsen before? This is great. 4 people. I did this poll with my office, and nobody had heard of him. So I'm firing all of them. Now there are thousands and thousands of others, but I'm not going to touch on them. I just wanted to touch on these because ultimately they're what allowed us to take our communication, our symbols that were bound spatially and temporally, and give them permanence and allow them to be stored. All these things that I talked about, right? And the magnetic drum is probably the most pivotal one because that became the basis for several types of technologies in the 19th, 20th, and the 21st centuries. Audio tapes, disk drives, LP records, etc. Any form of capturing sound, any form of capturing data was really done by the drum tape. And this is what Poulsen did way back in whatever that date was, 1890 something, 1899. He described, if you look at the patent that he has, and it's available on the internet, he described how data would be recorded on his magnetic drum. There was a long sequential piece of steel tape, and they were discrete. That steel tape was broken into discrete chunks of space, and in front of every space was a metadata block. He didn't call it metadata, he called it something else, a synchronization piece. And right after the synchronization piece is where he wrote his data. It might be some set of codes that needed transmission because it was data, or it might be audio, what have you. And so he at that point basically screwed us because for about 200 years now, even in the modern data center, this is essentially the seed of the format of our storage system. And here's where, everything just is crazy. Say you bought yourself that $1 million flash array because it's going to give you all this extreme performance. Well, guess what? When it actually stores data down on the storage layer, it still goes pretty much in that same format. So these things tend to stick with us for a very, very long while. So it's quite amazing. Now, tape itself, is great access. It had longevity. It could store it for long periods of time. In the in the early 20th century, they invented plastic, and so you could now magnetize plastic, and that gave you a much more durable medium, etc. But fundamentally, anything that runs in front of a head like this, that sequentially runs in front of a head, has some problems. It has a huge amount of latency because you have to sequentially read through everything to get to the data that you're interested in. It's sequential access only. There's no ability to do random access. And there's a big problem with something called the shoe shining overhead. Remember that for this to work, you also need a magnetomotor. You need a motor that can actually move things. And for a long time, we didn't have motors that would exactly stop where we wanted them. The motors would wind down slowly. So the data that you wanted, right, you'd read it, and then, unfortunately, as the motor slowed down, you'd spool more tape. As a result, you'd have to scrub back and forth. And that was called the shoe shine effect. And, it destroyed tape. There was a lot of friction on the heads and on the tape as a result of that. And this worked for many, many years, but in the mainframe era, as we were getting out of the mainframe era into the early minicomputer era, it became pretty clear that the sequential access nature of tape wasn't going to cut it, because IBM was now starting to roll out not batch-based systems, but interactive systems. And so a new form of random access storage had to be invented for this. And that happened in 1953 by the geniuses of IBM in San Jose. They invented the world's first hard drive. It was called the RAMAK, right? And what it did was, it basically took the gramophone idea that Edison had invented, 100 years before that, or 150 years before that, and essentially brought the idea from Valdemar of magnetizing, bits of steel, and instead of having a drum, he used a spindle. And this was in 1953, borrowing ideas that are 150 years, younger than that. Now, I'll give you one quick problem with the original gramophone. If you look at a gramophone record, right, the outer tracks have a larger circumference. The inner tracks have a slower circumference. So as your needle moves from the outer tracks to the inner tracks, it speeds up, right? Because and as a result of that, the speed at which they record are different between the outer track and the inner track. Okay, that is one of the biggest reasons why there's a VDI IOPS challenge. And the reason you're spending so much money on storage is because of the gramophone's physical architecture that we inherited because of the RAMAK and the invention of the hard drive. I'll get into that piece when we talk about virtualization next. But the RAMAK was an incredible thing if you think about it. For 1953, it was a 1,200 RPM disk. Today you can get 15,000 RPMs, which is still just about 10 or 11 times more than that. For a period of 70, 80, 80 years. We really haven't progressed much in the storage space. I mean, think about it, from 1,200 RPM to, 15,000 RPM, BFD, right? 5 megabytes of capacity. So that's one area where we've done well, obviously. Miniaturization, better materials, et cetera, right? And we've been able to pack more and more data. So today we have terabyte-sized drives, which is an order of magnitude more than what this thing had. But I mean, imagine the challenges in those days. There was no miniaturization, electronics, electricals. So they actually had hydraulic systems to move the read head back and forth. So when you wanted to move from sector X to sector Y, some oil was pushed through the pipes to move that actuator, to move that head from one place to another place. And it worked. It's an incredible invention, and has been the basis of modern data center storage for years and years, and it'll be around for a long time to come. Meanwhile, in another part of America, which is why I love this country and I emigrated over here, nowhere else I'd rather be, almost 85–90% of those inventions that we've talked about happen over here in this country. And there are good reasons for another BriForum session to talk about that. But William Shockley invented the transistor, which allowed the miniaturization of electronics, end of the vacuum tube era, and people at MIT invented random access memory. So suddenly we were out of the constraints of needing to seek data sequentially, and we could store data on these banks of charges that represented ones and zeros, and quickly go to the exact bank that we had some information on and pull that from there. So we got random access memory. And this now, for the first time, allowed us to create tiered storage. we were now able to place our active data, stuff that we frequently used, in the small chunk of random access memory, and then take data that was not accessed as frequently and put it on slower storage, like the RAMAK device. And we finally ended up having the architecture that represents the modern computer. We had a microprocessor filled with transistors for doing the symbolic processing. We had RAM, which was used for storing frequently used symbols and for short-term storage of the symbols. And then we had RAMAK and hard drives to store the symbols for long-term storage. Now, put that away, our modern data center doesn't look very different from that, except for some networking between these machines. But fundamentally, this is what we had. And fast forward 50 years, and the genius of Mr. Steve Jobs and people like him, and we have essentially the same thing now available in a convenient, easy-to-carry package like the modern computer. So this unleashed, of course, the PC era, and this is the last 20 years. There were some interesting challenges, battles. There was a RISC versus CICS architecture war in the 90s. How many of you remember that? Great times, lots of innovation. And this is when really Moore's law, came into effect, because Moore's law basically allowed the x86 architecture to become the default standardized architecture of the planet. So the x86 started as a personal computer architecture, but ended up, because of Moore's law, going upward and knocking the minis and the midis and all of them out and becoming the standard server platform. At the same time, it also went lower. It went underneath and became our personal computing platform, and not just on computers, but also on mobile devices. So incredible architecture, scales from all the way from little devices all the way to the data center. And it's really operating systems like Linux and Windows that allowed this Intel architecture to standardize and become the dominant platform for IT. So that sort of brings us to where we are today. And there's been, I literally compressed 5,000 years of IT, of symbol processing, of information technology, of storage, to give you a little bit of context as to the problems that we've had to solve as a society, as a culture, as Homo sapiens over the last 5,000 years, to only create newer, more interesting problems in the data center. So let's talk about that. So at this point, I'm going to switch and start talking exclusively about storage and starting to get pretty deeply into that. So this is the RAMAK architecture, the system that IBM invented with the first modern hard drive. This is what its architecture looks like. RAMAK was not a general purpose architecture. It was a very specific architecture for running one application, an accounting and control application. So you could still program it, you could still extend it, but it wasn't general purpose in the sense that you could install an application from your app store and run it on that, right? So what he had was an application that read and wrote data as a collection of data blocks. Same format that we had talked about before with the drum that Vladimir invented. And underneath it is an I/O subsystem, an input-output management system, that processes these reads and writes and puts them in memory. So this idea of putting things in memory started with really that RAMAK architecture. And then they had something called memory mapped I/O that basically took regions of that memory and mapped it to specific segments of the hard drive to a specific spindle. So it was a direct mapping. If you wrote to a specific address in memory, it went down to a specific location on disk, right? And this subsystem basically was a little bit of firmware that was in charge of moving the hydraulic actuators to move the spinning head one way or the other, to reposition the head and read and write that data. So that RAMAK system, state of the art those days, sort of like an EMC-V block, right, of that era. Total RAM, 16 kilobytes of drum memory and 5 megabytes of storage. And the reason it was only 5 megabytes was that the marketing department said, if you give them 10 megabytes, they won't know what to do with it. So let's just give them 5. So marketing departments have been screwing us since 1953. 600 milliseconds latency per record, only slightly slower than some of those VDI storage systems that I've seen out there. And its killer showcase was the 1960 Winter Games at Squaw Valley. And then its first customer was General Motors, who used this for their inventory management. So they got rid of a warehouse full of files and instead started to use this. And if it takes you about a second to retrieve a record, it's still probably order of magnitude faster than looking for files, pulling them out, and looking and changing things. Fast forward to today, the kind of desktops that you have in your PC, and this is the storage architecture. that sits within them. So very quickly, that did this, right? Why did it get so complex? For one simple reason, because it became a general purpose machine. It became a general purpose programmable system that could be easily extended by others who learned how to program it and delivered code that could be run on these systems. And again, here I'm just looking at the storage stack, just the piece that takes the data from the computer and puts it on storage, and look at how complex it's become. But this notion of virtualization, has been around for 35, 40 years, because if you look at what happened between there and there, right, is just layers of virtualization abstraction that came in that allowed that. So in the original RAMAK architecture, for example, there was some firmware, right? The memory mapped I/O directly mapped to specific segments of the hard drive, right? In this stack, we don't do that anymore, because there's a hardware abstraction layer that has a device driver, and that device driver actually manages things like memory mapped I/O, right? Pretty cool. So that's the green set of blocks over there, that device driver, the hardware abstraction that completely separates the hardware from the actual operating system and the application. The other thing you'll notice in the original RAMAK architecture, there's really not much of an operating system. All the logic of the operating system is actually in the application itself. So the accounting system is an operating system by itself. But over here, you now have a general purpose operating system whose specific task is to run programs as processes, right? And to provide various services like I/O, like display, like interactivity to them, right? So these are the different pieces in today's modern desktop application, desktop stack. So you've got applications, and applications use standardized interfaces to read and write files to storage. So the only layer that the application really sees is an API that says file open, file close, write, read in most cases. Unless you have a very specific need, you really don't need to use anything else that's a more direct mechanism. So those API calls hook into something called an I/O subsystem. And different operating systems, these are implemented differently, but the general idea is there's a virtual file system layer. And that virtual file system layer basically takes those file open, file read, close, all those calls, and maps them into direct memory pages. So the RAM that's on your system, a portion of that RAM is used to store data that's coming from the application as these read and write calls are made. And from there, the operating system basically takes those memory pages and hands them to a file system to manage. So this was another great invention in the last 30 years. In older systems, we basically managed direct blocks of data. And as a result, there was no standardization between applications. Every application had its own way of saying where the data offset was and how long it was and so on and so forth. The file system was the first real invention in storage that allowed us to generalize that whole thing and start managing data with the notion of files and directories and having a structured layout for it. So in the modern computer, the I/O subsystem basically hands it to the file system, and the file system imposes some structures like file and directory and allows you to structure how you store that data. And now you have metadata on the file system that also allows you to search, index, query, and do all sorts of interesting things over there. Now, underneath the file system is a bunch of other management that is done. There's the volume manager, right? And the volume manager's job really is to take the file system, that structure of files and directories, and map them to actual blocks. Which blocks? The same blocks that Vladimir Posin originally invented and said, this is the structure that I'm going to keep them in. Believe it or not, it's practically the same. So the volume manager provides that level of abstraction, and underneath the volume manager is the partition manager that allows us to take multiple disks, multiple physical disks, or maybe take one disk and split it into block ranges. So there's a specialization as you go from bottom to top. Each layer does one specific function, and in that process abstracts everything underneath it. So the beauty of this architecture is you can move things around. You can change the disk subsystem, and the application is not affected because all these layers of abstraction fundamentally allow you to do that. So even with virtualization, VMware, Hyper-V, we're essentially applying the same set of ideas, this abstraction of hardware that allows us now to emulate all these pieces in complete software and completely isolate the application from what is running underneath it. Virtualization is a fine art of lying. We lie to an application and tell it that its CPU is real. It's not. We tell it that its memory is real. It's not. And we tell it its storage is real. It's not. Lying has consequences, as we'll discover in the next set of slides. So when we virtualize, we're basically taking this stack, right? And we're putting an abstraction layer right underneath it. it sort of becomes this. You see what I did? I basically took this and made it one of the things on top. That's the guest operating system. So the operating system becomes a guest, and it runs alongside other guests on this thing called the hypervisor, and that hypervisor now emulates and provides resources to that application layer, and thereby fools the application into thinking that it's running on real metal. The application itself is completely unaware of what's happening underneath it, and as a result runs unmodified, which is what we want. We want it to be able to run unmodified for backwards compatibility reasons. If we wanted to use a hypervisor and we had to change our applications, well, that would be no good because that would be a waste of money. We might as well rewrite our applications in some more interesting ways. But in order to have backwards compatibility, you really need to have a full abstraction and a full set of rules to lie successfully to your guest operating systems. So this is what we've done in the last 30 years, in the last 15 years with the advent of virtualization. This is a direct result of Moore's law. Around about 1993, there was more than enough CPU cycles because of Moore's law effect of doubling CPU cycles and keeping the cost price constant, to the point that now on the desktop PC, around 1994-95, your application stopped taking advantage of whatever horsepower you had over there. Microsoft Word doesn't run any faster, whether you have an 8-core machine or a 16-core machine. It still runs just as badly as it did in 1995. And that's because really the applications on the desktop lost the ability to, there's just not enough complexity in those applications anymore to take advantage of them, right? And as a result, innovation on the PC really, started to dive. On the other hand, that same Moore's law and that doubling of processor capacity, when it went downward into mobile devices, made those mobile devices more powerful and capable of running more powerful applications. So you saw mobile platforms explode as a result of Moore's law. And on the server side, because of multi-cores, because of hyper-threading, you could really put this Moore's law effect to work because you could schedule more jobs. You could run more virtualization. You could run more guest operating systems. So the hypervisor is the first management innovation that allows us to infinitely take advantage of Moore's law because we can put more and more VMs on more and more cores as we add more and more transistors to our boards and increase the density of our IT infrastructure. So it's a very important innovation. But that innovation comes with a massive cost because it comes with its own set of challenges. I think I messed up my order of slides, but that's okay. So if you look at what's inside the hypervisor, the storage system of the hypervisor itself, this is your guest operating system, right? If you can see my mouse moving around over there, these are your guest operating systems. So that's one Windows desktop, that might be Windows Server, Linux, what have you. And it thinks it's writing to physical storage, but that physical storage is completely emulated as a file. It's a VHD or a VMDK, right? And that VHD and VMDK sits on another storage stack which looks exactly or pretty much similar to the one that was within the guest operating system, right? So there's another I/O subsystem within your hypervisor that's doing exactly what the guest operating system did. Take I/Os, put them in some section of memory managed by the hypervisor, right? And from there hand them to an internal file system on the hypervisor, VMFS, NTFS in the case of Hyper-V. And then underneath that again is another volume manager and another partition manager. And underneath that is a set of device drivers and this subsystem somewhere underneath this. So we've really not done an incredible amount of change over here. We've basically taken what used to work and simply encapsulated into another scheme that does essentially the same thing. And as you realize, storage starts to break down as a result of this because you can basically lie to an application and tell it the CPU is real, and it doesn't have to be, and the application will be fine as long as you can emulate the instruction set completely. You can tell its memory is real, and it doesn't care, as long as when it makes allocations, it makes deallocations, you do exactly what it expects. But when you lie to it that its storage is real, you have a big problem because the physics of storage is intimately tied to the operating system design itself, and we'll talk about that piece next. So what most people don't realize is that there's a complex set of coordination that is done in an operating system for data to get from the application all the way down to the physical storage layer. And that set of coordination is done using two mechanisms primarily, locks and queues. There are different types of locks, there are different types of queues if you're a computer programmer, but fundamentally those are the two constructs that we use for orchestrating and for managing the flow of I/O all the way down to the physical storage layer, right? Lock is very simple. We use it to protect concurrent writes and write collisions, right? So if I am working on a specific piece of data and I don't want somebody else to work on it, or I don't want another process to work on it at the same time, I put a lock on it. And whoever else wants to modify it has to wait till I remove the lock. So essentially, it's one person or using one resource at a time. In a queue, we use a different paradigm. We basically put things in a queue and then process them in the order that they are received. So in the modern operating system, remember that there's queuing going on within your guest operating system because it thinks it's running on a physical system. There are locks going on over there. So if you're using Microsoft Word, you're using whatever in your desktop in a VDI system, there's locking and queuing going on at that top level within each guest operating system. And then when it comes down in the virtual disk layer within the hypervisor, the same set of locks and queues are more or less repeated over here, right? So you have locking that happens at the vDisk level so that two virtual machines don't accidentally overwrite each other's files. You have locking within the I/O subsystem where if a data write is received, it's written to a RAM page. That RAM page is locked till it's actually flushed down to the file system. On the file system, data block ranges are locked so that two files don't get accidentally overwritten by competing processes. And then at the volume management level, block ranges are locked. At the partition level, and once you get to the partition level, you don't need to lock anymore. You start to queue things because you're dispatching them down to storage, right? And so it goes from there into the device driver. The device driver has another set of queues, usually in a virtualization system, a HBA queue, that then actually dispatches all of this I/O down to the storage system. And the storage system finally receives this in the storage processor, and there are a set of queues over there to reduce latency where all the I/O waits before it's actually serviced down by the disk head. So massive amounts of queuing, stacking, and locking that goes on in a virtual environment. Happens in a traditional operating system, but is exacerbated, as you can see, in a virtual environment because every single instance of a lock or a queue is aggregated and then sent down the same route all the way back to storage. So this is where the bottlenecking happens. So one of the things that people, I think, need to realize when they talk about storage and making their storage systems faster is it really doesn't make a damn difference if this becomes faster. It's a very important subtlety. You can take that and you can change that and move it from hard drive to flash drive, but the I/O path that all the I/Os have to take and the places where they're stopped and checked and locked and queued are still the same. So if you thought you bought that $1 million SAN that gave you $1 million flash SAN that gave you 2 million IOPS and it's going to make a big difference, it's very unlikely that you're actually going to see a significant difference. It's to the extent that you were storage bound, that you were IOPS bound, that you'll get an improvement. But the fundamental architecture of things doesn't change. The emulations haven't changed, the locks and the queues haven't changed. So as a result, you are not going to get a dramatic improvement in the performance of your applications. So I've got customer after customer who's bought tons of storage, who's bought expensive storage. They bought caching solutions, all of that stuff that's done on the storage array. But that doesn't have a problem. The problem is over here within the virtualization stack. The problem is much, much higher upstream. And this is where the bottlenecks are. And this is where we're kind of getting really jammed up and the solutions need to be found now. So in-memory storage is one of the ways of completely resolving many of these paradoxes that have come as a result of virtualization. So I did an experiment in my lab. I took a Windows desktop and I wanted to measure how much I/O it performs. So what I did was I put it on a RAM disk. Everyone knows what a RAM disk is, right? Some of you from the 80s might have even tried to put Wolfenstein or one of those games on a RAM disk because it used to take so damn long to load. So I created a gigantic RAM disk, put a virtual machine on it, and I ran it just so that I could measure all the IOPS. And what I found was staggering. So I did the typical things that people do when they log in on Windows. I launched Outlook, I launched Acrobat. Well, Acrobat launched itself and wanted to update itself 4 times a day. I launched Word, did some work in it, launched my browsers, ran an AV scan, and then Windows decided to update itself, pulled a bunch of updates down, and I captured a very detailed trace of everything that happens. Now, this is just one operating system, one guest VM that I'm working on that's doing all of this when storage is not bound, right? With those locks and queues only within that particular operating system. This is what happens. You see that, and I've only measured the peaks, by the way, over here. So this particular 800 IOPS is just showing you the peak I/O it hit when I launched it. The total amount of I/O that it actually generated is the area under that particular section, right? So 800 IOPS. When the AV scan at peak consumed 800 IOPS, but over a period of this, it actually consumed more like 10,000 IO operations per second. If you look at Outlook, pretty beastly thing, is that about 1,000 IOPS? So IO operations per second, it basically means that as long as you have that IO capacity, it'll happen in 1 second. So if I had an SSD that could throw out 1,000 IOs, all of these operations pretty much take 1 or 2 seconds, except for this one, the Windows update. That peak, to service that peak, if I had an SSD that serviced 1,000 IOPS per second, just that peak would take about 4 seconds, right? And so the point I'm bringing up is there's nothing inherently within Windows' architecture that throttle it and make it use storage more efficiently. There's nothing like that because these guys, because of backwards compatibility, because of the way these ideas have translated from the 1950s onwards, right? There are no throttling mechanisms that will use storage efficiently. So when somebody comes and tells you that your VDI requires 20 IOPS on average, you should stop listening to them because there's no such thing. Your VDI requires whatever IOPS it can take because that's how those paradigms that it's been designed around. The reason I bring this up is if you go back to the previous slide and you look at each of those VMs, right, that's on top, generating and trying to take as much IO as possible, right, you'll suddenly understand the magnitude of what the queuing and the locking does, right? So I'll give you one very specific example. Say you've got a VDI system or a virtualization system. You've got a hypervisor that's fiber channel attached to storage, right, FCSAN. The device driver layer is really a HBA that connects you to the SAN. That device driver has a queue depth of about 32. So 32 requests can sit in that queue and be serviced at a time, right? But guess what? We're emulating queue depths across. So each of these guest operating systems also has a disk, and each of those disks has a queue, and that queue depth is 32 too, right? So we basically have, say, in a VDI deployment, 100 VMs, each with a queue depth of 32, 3,200 IOs at any given point in time, waiting to go through the hypervisor stack, and then they wait at the HBA level because there's a queue depth of 32 over there, right? So the stacking complexity is phenomenal. The queuing latency is phenomenal. And so adding more fast storage down here doesn't change a damn thing. It'll change it only if your storage is so slow, right, that it can't keep up with even those 25, 30 IOPS or 40 IOPS that you've sized for. That's when your storage will make a difference. But fundamentally, adding faster storage won't change anything because we've got other problems within the stack, the locking and the queuing, and these aggregations are queue depths, right? And this tiny little gateway we have out of the computer at the HBA level just basically locks and blocks everything over there. So pretty scary stuff. That's what it makes me feel like when I first realized this about 5 or 6 years back. So this is what I call the virtualization storage crisis. It's not because your storage is not fast enough, it's because there are too many layers of abstraction and complexity between application and storage that are not understood. And yet we are designing our storage systems, our virtualization systems for things like the cloud for these massive deployments without treating the fundamental bottlenecks that are within the stack. One of the other problems that you have is when you have so many layers of abstraction between the application and the storage, the application's been fooled into thinking that it has physical storage underneath it, and so it writes to the storage like it's a real disk. And it thinks it has geometry awareness. It thinks it knows it's writing to a specific cylinder, a specific sector on disk, but it's completely emulated. It's writing to a file. That file itself resides on a data store. The data store itself resides on a virtual volume. That virtual volume itself resides on some sort of a LUN. That LUN itself is a bunch of disks that have been aggregated using RAID. And somewhere underlying all that is actually a physical disk, right, whose geometry has nothing to do with the geometry that the application thinks it's reading and writing to. It's a big problem, right? And the stacked I/O queuing we talked about, and there's one other part I'll talk about, this biggest myth in shared storage that will come about. And the solutions that we have in the industry today are just brute force approaches. Oh, let's throw more memory at this, let's throw more SSD at this.
But you do want that, the point you're bringing up is that the application is not a bit of a geometry of the data. But that's what we designed for, right? That's what we wanted.
Yeah. Yeah, absolutely. Backwards compatibility is what imposes that, right? And so if you want to keep that backwards compatibility, you have to fool it all the way. You can't lie, you can't do a half-assed lie, right? You have to lie, you have to be committed to the lie all the way. And it works in real life, works in virtualization. So,
We design an OS with the
Now you're getting into a topic that I really like. So I'll just talk about those 3 problems very quickly. Too many layers of abstraction. Like I talked about, the geometry awareness is completely wrong, but the point I want to really point you to is something I call hypervisor socialism. And boy, do we hate socialism in this country, right? Socialism here is what I mean, that the hypervisor actually does a damn good job of allocating resources from a CPU perspective, because it knows what exact instructions are being generated within each virtual machine, right? It can do a pretty good job of managing and scheduling memory, because it knows exactly what pages are being asked for within the guest versus what its physical layout looks like. But when it comes to storage, the guest operating system simply dispatches blocks, reads, and writes. And all the hypervisor does is just translate them between the 2 layers of abstraction. It doesn't actually understand the content or what I/O is actually being generated. So as a result of that, the hypervisor simply implements a fair scheduling algorithm. It basically takes the I/Os that are generated by different guests in the order that they're received, packs them together, and sends them down. So as a result, if you're in a VDI environment, right, and I'm launching a massive spreadsheet because it's got my data, it's got my sales numbers for the quarter, whatever, I want that to load as quickly as possible. And my annoying colleague next cube has running an AV scan. The hypervisor doesn't know better. It doesn't know that I'm launching Excel, that he's running an AV scan. It simply takes these I/O requests in the order that they came and dispatches them in the order that they came. So as a result of the socialism, every I/O is treated equally and everyone is penalized equally. It's not such a big deal when your densities are not high. If you've only got 10 VMs on a hypervisor, it's not such a big deal. But when you do VDI, you have 50, 70, 80, 100 VMs, 150 VMs on a hypervisor. And that's where the time slice given to each guest reduces. And this hypervisor socialism really causes a massive VM performance issue. Couple that with the previous picture I had of all the different layers of stacking, locking, queuing, right? It's even a miracle that these things work today. I'd really put it as that, as bluntly as that. This geometry awareness, and this is why it's such a big deal, and I'll answer to a point that you raised. So, Windows operating system, Linux, all these operating systems fundamentally have been designed for spindles, for spinning platter, right? And if you look at the physics of a spinning platter, it's no different from that gramophone that I talked about earlier. The tracks that are on the outside have a bigger circumference, right? And so you can store more data on the outer tracks without needing to reposition your head, right? You can get, X amount of data on the outer circumference, but you'll get only a fraction of that X on the inner circumference because your read head has to reposition. And repositioning is what causes latency. So Microsoft came up with most operating systems have this wonderful innovation where the operating system will watch what the hot active data is, what its actual location on disk is, and then migrate it outward so that you can get long sequential reads and writes on it. So popular data is constantly evaluated and hot data is moved out, right? Works beautifully in a physical system. So if you've bought a laptop or a PC with a SAS or a SATA drive, it probably improves your user experience by about 100%, 150%. It actually makes those $400 Fry's PCs and Best Buy PCs usable. This is that one feature that does it. But when you virtualize your storage, you put it in a virtual machine, your virtual machine doesn't know that it's a VHD or a VMDK. It still thinks that it has physical geometry that's laid out this way. So it starts to move data between what are imaginary inner tracks and imaginary outer tracks, right? So there's a tremendous amount of overhead that comes from fooling the operating system into thinking it's running on physical hardware from a storage perspective when it's actually running on virtual hardware, really. And there are lots and lots of optimizations like this. There are about 14 odd optimizations like this that are really designed to give more performance on spindles, but end up taking up most of the capacity of a storage system. So I don't have a slide on this, but I usually show this to a lot of customers. We did an experiment where we captured data from 100,000 desktops spread across about 30 or 40 of our customers and try to figure out what is Windows doing with all its data. And what we found was that Windows was basically wasting most of the I/O that was available on the storage system, moving imaginary blocks back and forth. And it's simply because we're fooling everything. I'm going to quickly. So this is the myth, the great myth of storage. Most people think storage works like this. That when they buy that fiber channel SAN with an SSD array, it looks like this. There's a set of lanes that are taking data into the array, and there's a set of lanes that are bringing data back into the storage, back into the servers. It sort of looks like this. All of this is happening concurrently. Not really. It looks like this. And this is one of the most underappreciated facts of storage, that all storage is implemented using an elevator style algorithm. So just like people wait to get into the elevator, and the elevator can only go one direction, either down or up, all I/O is either going down to the storage or coming back, and every I/O has to wait its turn over there. So you can buy a super fast array at the other end, right? But the fabric that connects that storage to your servers still is bound by the laws of the elevator, because it can only move data in one direction, not in two directions. So hopefully at this point you're feeling very, very depressed, and you're ready to hear about how in-memory storage solves this. I won't get into the CAP theorem because I'm tight on time. I'll just quickly jump out. Oh yeah, actually I do want to do this. So CAP theorem is simply a mathematical theorem that was proven by a guy called Brewer that applies to storage. It fundamentally says storage should do three things: provide you data consistency, data availability, and performance, right? But you can only have two out of these three at any given point in time. You can't get all three, and he's mathematically proven. So storage systems, basically shared SANs and NASs, prioritize consistency and availability over performance, whereas local storage systems use consistency and performance over availability, right? So the challenge you have is when you implement shared storage systems, how do you get more performance? And the only answer the industry has to that is just add flash, right? But as we talked about before, adding flash doesn't do anything because the locks and the queues are up there. All that stacking, really doesn't help because it's all within the hypervisor, and the flash that you're adding, is not at a layer that makes sense. So flash is not the answer. Can flash arrays help? Yes, they do help. If you're genuinely IO constrained, they can give you a lot of IOPS, right? But flash has its own set of challenges. Capacity is one, for example. And to get around capacity, a lot of flash vendors have put in compression, deduplication into the arrays. And that deduplication and compression is done such a way that a lot of the I/O capacity of the array itself is chewed up by the deduplication compression algorithms. So this is a real-life example of a commercial product that I've seen and done some tests with. This is a 40 SSD drive, 150 gig, 2 million IOPS rated system. You turn on deduplication and compression, it drops down to 200,000. So my question was, where did my 1.8 million IOPS go that I paid for? Where it went was in the deduplication and compression cost of flash. So do converged infrastructures help? Because that's the other big thing that everybody's talking about. Let me do converged infrastructure. Let me bring storage and compute together. Like, that's going to magically solve something. You still have the same hypervisor, the same stacking, the same I/O queuing, ordering. Hopefully by now you appreciate that nothing has changed. We've just fundamentally moved the big Lego blocks underneath them. And no, they don't help. Nothing has changed from the architecture perspective. In fact, there's more performance penalty because data has to now be replicated across these multiple nodes, and that means there's more I/O stacking and queuing going on. Another example over here that we've done tests with, 4-node converged unit with Fusion IO SSD. Each Fusion IO can do at least 100,000 IOPS. So 4 cards should give you theoretically 400K IOPS. Guess what it actually gives you? Less than 50,000. So my question is, where the hell did my 350,000 IOPS go? It went in the replication cost. So fundamentally, you can't beat the CAP theorem. The CAP theorem is the E is equal to MC squared of the storage universe. So where do we go from there? I like Gandalf. I'll give you these presentations to download later. But Gandalf made a very, very important insight. He basically said that we're ready to go into a new world of in-memory storage. Well, he didn't call it in-memory storage, but I call it in-memory storage. But what in-memory storage is this idea of using RAM that's on the server as the primary storage layer. You use just the RAM on the server as storage. All data is kept within that RAM. It's kept in the main memory because that's the main storage. You're not tiering, you're not moving things back and forth. And depending on the type of data, you can have different types of commit policies. You can basically commit data down to physical storage if you want to have persistence, or you might just choose to replicate it among other nodes and keep it there for types of data that are very transient in nature, right? And if you don't care about volatility, you can do lots of temporary reads and writes, stuff that requires a lot of fast, quick storage. You can do all of them in RAM. And you can address the volatility challenge by using things like non-volatile RAM or transaction logging or replication. But why RAM, you might ask? Well, for 2 reasons. Now we're finally at a point in the computer industry where there are meaningful amounts of RAM on every server. We're talking about servers that have 256 gigs, 384 gigs, 512 gigs of RAM. It's really, really fast. And you might have a question, doesn't caching already solve this? Well, caching doesn't. Caching was a technology that really improves the performance of a storage system when there's a one-to-one mapping between the application and the storage volume. But in virtualization, a storage volume is shared by many VMs, and so caching completely breaks down because that's not the architecture that caching was designed to solve. So caching doesn't help, and if it does, it'll only help you in accelerating some of the reads if they're in the cache. They can't do anything for the write IOs that are generated by virtual workloads. So, caching is not the answer. Throwing a PAM card is not going to help you when you're deploying virtual machines. And, the question you might have is, well, exactly how much RAM do I need for all of this? And for those of you who are Redditors, all of this stuff should be pretty common. Well, here's the problem with RAM. There's not still a lot of it, because even if you take 512 gigs of RAM, if you have a VM that's 50 gigabytes in size, right, you can only fit about 8 of those VMs before you run out of storage. So it's not very practical. So there's a capacity problem, because VMs are huge, and there's a volatility problem, because you might lose data. But this is where Moore's law, again, comes to our rescue, because we can use the residual power of the CPUs that are available on these gigantic multi-core systems, right, to do things like inline deduplication, inline compression right there within the hypervisor, and address the capacity issue by deduplicating and compressing those 50 VMs. Instead of chewing up 500 gigs of space, they only chew up a very small fraction, maybe 90% less, just 5 gigs of space. And so we can put more VMs on that RAM. And then we can address the volatility by using smart algorithms, by taking what's in the RAM after it's been deduplicated and compressed, and synchronizing it out of band down to storage, or replicating it to other nodes, or logging it as transactions asynchronously down to the physical storage layer. Now, for a lot of us, it might seem like in-memory is all, science fiction. It's not there, but it's actually been there for a long while. A lot of the largest websites in the world run using in-memory storage. So Redis, for example, is an in-memory technology, really, really cool. And it's used by places like Twitter, Instagram, Facebook, etc., because they really want to give you that amazing user experience that you log in, you immediately get your feeds, etc. It's not possible without something like this. Oracle uses in-memory storage in its Exalytics product that's a part of Exadata. SAP has rewritten the entire SAP family of products using in-memory storage to allow real-time analytics. It's called HANA. VMware has a product called SQL Fire that's an in-memory storage. And Microsoft SQL Server 2014 comes inbuilt with in-memory storage as well. And then these are all application-specific infrastructures. If you want a storage infrastructure that allows you to accelerate all your VMs, regardless of what the VMs are, whether it's VDI or virtualization, Atlantis has the Ilio product that does in-memory storage for virtual machines. So fundamentally, I just want to make one other point before we open up for questions and answers. How does this in-memory storage fundamentally change the game? How do we break the cap theorem where you can get only two out of the three? Well, how it solves it is by breaking it into 2 dimensions. The in-memory storage layer on the server gives you consistency and performance. And in conjunction with shared storage, your existing SAN or NAS enforces availability and consistency. So it's broken into 2 distinct tiers, and the cap theorem is resolved by giving you 2 of the 3 in the server tier and 2 of the 3 within the shared storage tier. And so that's how you resolve it. And so now, your question might be, how does throwing more memory solve this? Am I not just doing the same thing as adding more flash? Well, you're not, because the in-memory architecture is very, very different. You don't need all these layers of abstraction within the hypervisor. The in-memory architecture actually looks like this. It's much simpler, cleaner, and is designed without a need to do the kind of locking and queuing that comes in the general purpose architecture. So this is what an in-memory storage architecture looks like. These are your VMs on top. There's an IO subsystem that's underneath it, and underneath that is a pseudo file system. You don't really use a full file system. You don't need a real file system. As long as you can pretend enough that it looks like a real file system that the application can read and write files on, you're good. And underneath that, you implement your IO optimization technologies, deduplication, compression, replication. And the beauty of this is there is no locking in this architecture at all. All there is a little bit of queuing when that data goes down to storage. And all of this data is all kept in memory locally, so you can address it, you can read and write it as fast as the host bus will let you. And that means that your latency is no longer measured in milliseconds. It's typically measured in microseconds, and in a couple of years in nanoseconds. In microseconds to nanoseconds. So we're talking about a whole new realm of possibility with these in-memory storage architectures that are on the horizon, that are there today, for example, for virtualization. But this is what's fundamentally going to change the game when it comes to storage. Yeah. So one downside, though, is that the locking and queuing is still within the guests. Remember, we didn't change the guest for backwards compatibility reasons. So there's still locking and queuing within the guest, but the hypervisor itself imposes no penalty as a result of this. I'm going to run out of time unless I touch on 2 slides, so let me just jump over there and then open it up for any kind of Q&A. So I've done some extensive testing on in-memory storage, and this is an example of how you can take 4 blades, the memory on those 4 blades, aggregate them to make them into in-memory storage, and get just a shitload of IOPS, 750,000 IOPS coming off just 4 blades using residual RAM while there are guest operating systems running on them. No loss in translation, no RAID penalties, none of that stuff. What you see is what you get, 750,000 IOPS. 750,000 IOPS is a lot of IOPS. You can run magnificent amounts of applications on that. This is an example of the kind of change that happens when you use in-memory storage. You don't need to add any hardware, but you can accelerate your existing application, databases, Exchange, et cetera, by 5 to 8 times without adding any additional hardware. And this is the benefit of in-memory storage. This is the TPCC benchmark, which simulates data warehouse activity on a database. If you run this on typical data center storage, I've used a NetApp 20 disk aggregate as an example over here. Look at the choppiness of that I/O. The I/O stalls frequently when the storage system gets busy. Same exact workload running on in-memory storage. There is no choppiness, right? It stays within a very tight, narrow band. And this creates all kinds of new opportunities to give service level guarantees, to do resource locking, et cetera, with storage. So big benefits to VDI, obviously, no IOPS limitation. You can enable search and indexing, all those kinds of features. But there is a dark side to in-memory, right? And the main challenge with in-memory is that all those VM bottlenecks are still over there. If you don't have deduplication and compression, for example, Redis doesn't, you're not going to get a lot of working set into that memory. You need a lot of memory in those situations. High availability is also very challenging to achieve. And you trade off buying servers for storage, right? But servers are a fraction of the cost of storage, so much better thing to buy. Last bit, what I'm excited about for the next few years, I'm very excited about a killer new way of doing flash for servers. It's something called memory channel storage. It's the ability to take flash and put it directly on the DIMM slots off your server. And there's a company called Diablo Technologies that has done something really cool over there. I'm very excited about this because this now allows us to have servers with 10 terabytes of memory available directly addressable by the CPU bus. I'm very excited about non-volatile memory, and I'm very excited about erasure codes, which is a new form of spreading data around for redundancy instead of using RAID, which is creaking and really at the edge of its envelope. So I'd highly encourage you to go and look at Diablo Memory Storage, which has done some really cool work where you can actually take flash and instead of attaching it as PCI Express, you can actually attach it as a DIMM slot. And so, if you take some of those new blades from HP or UCS that have 84 DIMM slots, you can literally stick a terabyte on a DIMM slot and so have something like 85 terabytes within a server directly addressable like memory. It's pretty cool. So this allows us to have between 1 to 10 terabytes of RAM on a server in the next few years. It's pretty crazy. I'm very, very excited about non-volatile RAM because I think flash is a stopgap technology. It's not going to stick around long enough because non-volatile memory is going to come and kick flash's ass. Flash is an extension of our old way of thinking that we have tiers of storage and it's just a faster tier of storage. But non-volatile memory fundamentally changes everything. Just imagine that your memory was completely non-volatile. It would change the way you program. It would change the way applications are written. So there are 2 fundamental technologies that are vying for this. There's one technology called memristor, and another one that's a variant of memristor called resistive random access memory. These are now in early commercialization. So by 2015, you should have servers that already have a chunk of non-volatile memory running on them, right? And what's going to happen by 2020, per my calculations, is that you'll have an NVRAM of about 512 gigabytes within each server. And when that happens, our biggest challenge will be what to do with all this memory. So one of the predictions I have is that we're going to have the advent of what I call the NAM, the network attached memory model, where we're going to consolidate memory like shared storage, right, centralized memory, and then dispense it to hypervisors and operating systems on demand. These are my predictions for 2025. Servers with 256 cores to 1,024 cores. Cloud service providers will have between 1,024 to 8,192 VMs on each host. Local RAM of about 16 terabytes to 32 terabytes per server node. Shared memory of about 1 petabyte using these NAM technologies. Erasure codes instead of RAID. And zettabytes of storage at the back end. And Windows 2025 will probably get rid of Metro UI by that time. So lastly, software will not be written the way we think of it. Our whole architecture of writing software, even simple things that you learn in Computer Science 101, variables. You declare a variable, you change a variable, and then when you want to save it, you take that variable and write it down a disk. There's no need to do that when you have non-volatile memory. So you'll have new programming techniques available where all variables become immutable. So essentially, the snapshotting idea that we have at disk level will come to the memory level, and we will be able to capture the state of an application variable by variable, nanosecond by nanosecond, and be able to replay an application back and forth at massive scales. It just changes the game. ACID semantics will completely dry, because of this ability to do variable by variable immutable changes. And finally, these are my predictions for the top 2 sessions at BriForum. Everything changes, but nothing changes. We'll still be talking about how to fix printing in XenApp 15.5. We'll probably be talking about how to move user profiles from Google Glass to, I don't know, to your contact lens or something. And finally, if we're still talking about Windows, someone please shoot me. Thank you, folks. Thank you very much for your time. This was... Any questions?